I think we can start. All right. So good afternoon, everyone. Welcome to the 9th lecture in advanced computer architecture. So this is hopefully fascinating topic about how you do or how you perform processing in another place where we're supposed to do it. We're supposed to use the CPU to perform all these operations, but we discussed last time that this is sometimes can be a very expensive option to do the processing in the CPU, because we agree that the whole computer architecture that we have today is compute-centric, right, rather than being data-centric. So we are trying to move everything from the memory all the way to the CPU, which cause a lot of problem in terms of data movement. And for that, we have to pay for the energy, total energy of the system. We have to pay for the execution time, because we pay penalty every time we have a miss. So we have to go to the storage, fetch the data to the main memory, all the way to the CPU. And we discussed last time several options how we perform processing in memory, but all the examples that we went through were about simple operation. Do you remember any of those simple operations that we performed inside the DRAM device itself? And then the OR, excellent. What else? Copy a row, the entire row, a cache row could be, or a DRAM row in the subarray. We copy it inside internally, and we have three options to copy. Either we copy it inside the subarray, or between subarrays, or between banks, right? And we see different costs of doing so. Excellent. So today, we'll be talking about more interesting topic, which is how to perform more complex operations. So we see through bitwise and OR. We also went through the copying some data, but today we'll discuss more about complex operations. So this is just a reminder for all of you for the needs to do something really innovative, something different than the things that we've been trying to do for over 80 years with the Von Neumann model, right? So we discuss being intelligent in every aspect in terms of the cache itself, the memory controller, the DRAM device, the storage devices, and so on. And we said it's not only about compute and memory. We also want to do something fundamentally new at the storage size. And we see something related to how we develop synthetic DNA molecules, and we use them to store some bits, right? So do you remember the story of DNA storage, A, C, G, T? Then we can encode A as 2 zeros, 0, 1, 1, 0, 1, 1, right? And we can use the combination of those binary bits to encode any kind of text. Could be a movie, picture, could be also a whole book, right? Just in a small amount of DNA, you can store all of these. This is something new. It's been in the news, I think, today or yesterday. So I would like all of you to check it out. Go through the link and check what's being fundamentally different with the cooling system. So we talk about the architecture with the compute units. We talk about the memory. We talk about the storage. Now, this is something totally new on how you enable to cool down the silicon itself, the processor, much faster than before. So this is something really we don't see before, something fundamentally different in a sense that those cooling liquids is injected between the transistor itself. It's not isolated. It's not a fan in top of the CPU as we see traditionally in those computers. So it might be really interesting to check out the link, go through the material, try to understand what's happening, and maybe you'll do some research about it. All right. We saw several forms of how we can perform processing in memory. There were 5 forms at least. There could be many more other options. One of them to perform some computation in the memory controller itself. And remember, the memory controller is located at the CPU chip itself, okay? It's separated from the DRAM module. You could also enable the computation to be done inside the DRAM device by having a PIM or compute processing core inside the memory itself. You could also leverage the operation or the analog operation of the DRAM device and perform computation using those operations. Some of those operation is reading a row, pre-charge, right? Activating one row. So if you follow these 3 steps, you could have some kind of computation. We saw 2 examples of doing so. One of them, the row clone, right? How we copy the entire row using just by different sequence of the 3 operations that we know, which we start with activation, next read or write, right? And then the third one is pre-charge. Excellent. What do we do with the pre-charge? Try to update the charge in each row, because this operation, remember, it's a destructive. What does it mean? Destructive means will destroy the charge in the row. So we no longer have that charge because we are sharing it with the bit line, right? So if this full VDD, we have it half VDD or half plus some margin for that. The pre-charge is responsible for returning back the original charge to the row, okay? But of course, sometimes we amplify that charge. So even if it is like half VDD, right? Plus some margin, it could be theta or delta, right? We amplify that to full VDD because it's exceeding the threshold. And when we charge it back, we have it as VDD. So we are not just restoring the charge to the row, but rather we amplify it first, and then we push it back. The other really modern way of doing processing in memory is to have the 3D cube. So where we have the stacked memory on top of each other, and then we have one layer of logic layer that you can reconfigure for the computation that you would like to do. So the computation is not happening inside the DRAM chip itself, but rather in a separate logic layer that you can reconfigure and do whatever computation you want. And this is basically, we said, in most of modern GPU, you have what we call as high bandwidth memories, okay? So most of these cubes exist already in today's GPUs and FPGAs. The last form of processing in memory, we might have an example on that, which is near storage processing, which is inside the SSD device itself. So remember, inside the SSD, we do have a DRAM, okay? Inside the SSD, we do have a DRAM, although the computer requires a DRAM to be in the middle, right? Because something like temporary storage, or what we call primary storage. And we move the data from the SSD to DRAM all the way to the caches to the CPU. But still, we need a DRAM inside the SSD to do. What is the purpose of DRAM inside the SSD? Normally, just like 1 GB of DRAM. It's not really big. Maybe at most 2. So we can use it as a cache, okay? Just a way of caching the huge data that we have the SSD. So we need to move all the time pages out of the SSD to the DRAM, to the original DRAM outside the SSD device. But to do so, we might have some congestions. So we have to have a buffer where we keep all those pages and then keep moving them to the DRAM whenever we have availability. So the processing inside storage is happening at the controller itself, the SSD controller. Here where we have the DRAM inside the SSD device, this is the entire SSD. We have some cores, simple cores for the controller to control the commands when to read from the SSD and when to write. This was the example on row clone, how we copy from one row. We have to activate 2 rows. We activate one of them, we move the charge to the sense amplifier. We activate the second, we move now from sense amplifier to the second row. This is how we copy data quickly. We saw 3 examples, as I mentioned. One of them, how we copy within a subarray, how we copy within subarrays, and how we copy between banks, okay? This is the paper. And the next paper we discuss about and or operation inside the DRAM device. How many rows do we need to activate to perform and or operation? Someone says 2, someone says 3. 2 or 3? How many of you says 3? How many of you says 2? Yahin in the middle. Not 2, not 3. 2.5? All right, so we have 3. We need to activate all the time 3 rows. That's how we will have a majority voting. Okay, so if 2 of them agree on one charge, that will be the output. Okay, at least 2 we should have, so that we can agree on a value to be in the output. And we activate all of them, and we said whenever we activate rows directly, we share the entire charges in those rows. Okay, so in this case, what is the charge stored in the 3 of them? You have in the first VDD, full voltage, right? The second, again, VDD, so full voltage. In the third capacitor, you have it empty, right? 0. So we share 3 of them all together, meaning that we add them up. That is 2 VDD. And then we divide over all rows. We have 3 rows, right? And then that will be 2/3 of VDD in each of the capacitor. This is once we activate the row itself. Now we activate, we get 2/3 in each of them. 2/3 meaning that it exceeds the threshold. If it exceeds the threshold, means it is acting as if it is 1, as if it is binary 1. Then the sense amplifier will understand that this is 1, will sense it and amplify it, and then we'll push for VDD to do the pre-charge and charge all of them back to full charge. Now we have a 0 here because this is a negation. This is an inverter, right? So over here we have 1 because the sense amplifier already understands that we are exceeding the threshold over there. And we have a 0 over there. And we discussed last time, you don't have to worry about those 2 inverters, why we need both of them. But remember that we are using a differential sense amplifier. That's why we have 2 inverters in the sense amplifier itself. Now, how we could leverage this for and or. So we got this equation. We extracted from this. And this is happening based on the option we will have over there. So we said all based on C value. If C is 1, then we will enable the OR. And then we will perform OR operation in this logic. If we have C as 0, then we will enable the other operand of the equation. And then we will have AND operation instead of OR. Okay? This is just a quick reminder. Hopefully, you still understand everything because we are going to reuse it now. This is we said AMBIT. We call this technique AMBIT. AMBIT has 2 papers, one of them in 2015 and one of them 2017. So everything we saw so far was published in 2015, meaning the earlier version of it. They extend it, they improve it, and they add the NOT function or the inverter to the operation. And this is what we will see now. Okay, how we perform NOT operation? Very simple. Remember, we talked about differential sense amplifier, right? We move the charge. We already know it's 1, but in one side of the sense amplifier, we could know that it's 0 because we have the negation value of the original sensed value. So this is the sense amplifier. This is already exists in all DRAM, so nothing new over here. However, we don't have any control where to read. The only way we can read is before the inverter, which will go to the column decoder, so we can read which column coming from the row, right? This is what we have. We don't have any access to the value over there, for example, after the inverter. So how we are going to take the negation of the value already in the sense amplifier? And that's simply what they propose. So just connect a wire to this point where you got it after the inverter and store it back in another row. So just for every sense amplifier, meaning that we store 1 bit, you have to connect through a wire back to a new row to get the negated value or the inverted value out of the sense amplifier and store it in a new row. Okay, this way you have the original data in one row, and you can sense or you can amplify it and pre-charge again, and also you have the negated one. So they call it D word line and N word line, which is the negated value. Okay, so what they add or the overhead of this operation is that they need to consume 2 rows per inverter operation. So 2 rows, normally. Why 2 rows? Because we need to maintain the original value in one row and the negated value in another row. Do you have any question? All right. Hopefully, if you are, how many of you still remember combination or logic gates from digital design? How many of you still remember logic gates from digital design? Do you still remember how you do simplification? Excellent, almost everyone. So now, by using and, or, and not, can you perform any logic operation? Are you missing something? By just having these 3 basic gates: inverter, and, or. Think about it. What do we need for NAND, for example? Not an AND, right? What do you need for XOR? What do you need for NOR? Right? So you can build basically anything from these 3 basic gates. So this is a very nice job having the 3 gates already done in the DRAM. And remember, the granularity of operating those is what is the smallest amount of cells that you can do with AND operation. Can you do 1 bit by 1 bit? Can you do 4 by 4, 8 by 8? What is the smallest granularity that you can do? Always a bit. Size of? Yeah, what is the AND gate? This is the question in another way. 2 inputs. What is the size of the AND gate here? How many inputs we perform in parallel all the time? 3. You are close, but you need to multiply that number by like million maybe, or yeah, you are close. 3 something. We activate 3 rows all the time, meaning that we don't really activate 3 bits, but we activate the entire row. So we perform AND operation or operation or not operation on the entire row. So if the row has 1024 bits, that is the size of the AND operation. So 1024, for example, with 1024. These in one row. This is another row. We have all of them in OR gates, for example, or in AND gates. Right? That is the smallest granularity that you can have a bitwise operation on. Okay? This is clear. Still have some doubts? Naeem? So we are not doubling the rows. We are not adding something new. We just leverage the existing rows in the subarray to perform this operation, except for the NOT operation. Now we add a new row over there. That's the overhead. Okay? For AND, for OR, we are fixing those rows which already exist in the subarray just for performing AMBIT. Okay? That is another overhead. We discussed last time that we need all the time 5 rows fixed for AMBIT. Why 5? We need the A, B, C in the previous slide, right? A, B, C to perform that equation. We also need the controller. Excellent, 0 and 1s, right? The controller. The controller, based on C, either we perform AND or OR operation, and the controller takes either 1 or 0, right? So we save an entire row, complete row, because remember, we cannot send just 1 bit of 1 to activate C. There is no bits here. There is entire row. Either you take the entire row or you don't take it. That's the deal. Okay? So if you want to send 1 to the C, you have to activate the entire row with 1s and have that copied to C. Okay? Now the entire row of C has all 1s. And then in this way, we enable the OR operation between A and B. A is not a single bit. A is a complete row in the subarray. Likewise with the B. Okay. Hopefully those fundamentals clear. This is some results. You can see Skylake is already old processor. We have a GPU. This is no longer there. HMC is the earlier version of memory cube, the HBM. It's no longer in the market. AMBIT in AMBIT 3D, which is based on the HBM or HMC structure. 3D stacked memory on top of each other. So basically just the bandwidth is higher. We have more banks, more subarray. Now we can see the throughput, which is the number of operations per second that we can perform in bulk. Remember, the and or are very good in performing something really in bulk, meaning that the whole shot of 1,000 of 24 bits or 2,000, 3,000 altogether, depending on the row size, all of them will be performing AND operation at one shot. Okay, so you can think about it as SIMD lane, something huge. What is SIMD? Single instruction, multiple data. What does it mean? It means if you want to perform like 5 times 3. Okay, you want to calculate it, it's 15. You all know that, right? No? This side doesn't agree. Hopefully I will convince you. Okay, yeah, please close laptops, everyone. Please do it quickly. Please. Businesswoman in the back, please close your laptops. Okay, amazing. So we perform one multiplication operation, right? Now we want to perform another multiplication operation. So for example, 2 times 10. What is the result? What is the result? 20, right? Now I want to perform again another operation. 1 times maybe 23. It's 23, and so on. So we see that we perform all the time multiplication, right? So if we perform multiplication, if the processor is enabling something we call SIMD or SIMD, single instruction multiple data, we said, okay, this is operand number 1, this is operand number 1, this is operand number 1, this is operand 2, operand 2, operand 2. Now take all operands 1 in one vector, one large array. So we will store like 5 somewhere in that vector. What else? 2 and then 1. Now this is one vector. Now, of course, the width of the vector is configurable from one processor to another. For example, if we are talking about Xeon, Intel Xeon, the latest one is to use something called AVX 512, meaning that the register, each register is the size of 512 bits. So that's the size of everything we have here. Now it's up to you how you divide that space. Normally we divide it 8 bits for value, but you can go 16 per value, 32, it's up to you. Now assuming we have 8 bits for that, so you still have like large space here to fit more values, okay? Now we use another register, again of size 512, and we store all the operand number 2, 3, 10, 23, and so on. Now in one instruction, you could use for AVX, and this is like API, so you have to respect the order of those operation and the name of the function and all these things, okay? You can call AVX 512 with operation of and just give it those 2 vectors, and that's it. Just tell it, for example, and sometimes normally the instruction has the size to understand like what are you looking for, what is the size of each operand. So sometimes normally it looks like this, and underscore 8. Sometime here we wrote AVX, and then you give it like X1, which is this register, X2, and then put the result in X3. So in one instruction, single cycle, I'm performing 3 multiplication, not only 3, but could be really more, depending on how many numbers you could fit in that register. Okay, this is what we call SIMD instruction. Why we were talking about SIMD? Yeah, I forgot the context. Okay. Yeah, So that was one example of how you do AND operation in bulk. Okay. Now, when we talk about AMBIT, the granularity is not 512, right? It's much more than that. It really depends on the DRAM that we are using, which is the entire row size. So at least 1 kilobyte or 1 kilobit, sorry, that would be the minimum row size normally in most of the DDR. Okay. So you can think about the difference between performing AVX, which is the fastest possible you can get out of a CPU, performing AND operation in parallel in multiple operand, with AMBIT, where you can perform in bulk inside the DRAM itself. You can see the speed up. But if you want to do something small, like at smaller scale than this, then AMBIT is really a waste of cycles. Okay, because you are loading smaller amount of data to the row and then perform that for the entire row, which you are not going to reuse. All right, so it was a very good use case where we showed the benefit of using AMBIT, because remember, AMBIT is very simple bitwise operation, just AND and OR and NOT. And the best use case that we show in the paper, something called bitmap index. How many of you are aware about bitmap index or bitmap indices? How many of you do database? Database management, database queries through web design. Have you ever dealt with any huge data, big amount of data that you need to query in short time? No? How many of you didn't hear about database at all? Okay, so, all right, so maybe we can see this example. I'm not sure if it's clear. Maybe you can try to zoom in. You like that? How many of you are aware about this? There's 3 tables in database, right? And in one table, you have the countries. In the countries, in each of the country, you have the number, okay? You have here the male, female. You have also the age, okay? So 3 tables. You want to perform quickly which person is living in this country and has this age. How you would do? SQL query, excellent. Now, for this kind of question, if you ask, does it exist, does not exist, normally we do a bitmap. Bitmap means you convert all tables into binary data, okay, just bits. And then you can use bitwise operation to apply it in bulk in all tables. For example, if you are looking for joint operation between the 3 tables, meaning that whenever the condition is true among all of them, like being male, being from this country, being with this age, then that is a really good use case of bitmap. And why it's really good is that because you are looking for having that condition true among the 3 tables, meaning that you just do AND operation between the 3 tables. That's it. Whenever we get the result as 1, meaning that we satisfy the 3 conditions. As simple as that. And AND operation is really quick. You don't have to go for loop, for example. You don't have to do it sequentially. You can just AND everything in the 3 columns and done. How we do it first? As I said, we have to convert into binary. So we get something like that. Just convert everything into binary, and then just do the AND operation between them. As simple as this. Whenever you get 1, or you can do OR, for example, if you are looking for, here we have like all people where their age between 19 and maybe something else, which is 23. Okay, so we are looking for all people having that age, or this age, or this age, or this age. This is another use case. So you can do OR operation between all of them whenever we have 1, meaning at least one of these conditions was met. Okay. So they tried that for those kind of use cases with AMBIT, and then they said we require about this much of OR operation, this much of AND operation, but also we need the bit count. What is bit count? Like after you do the AND operation between the 3 tables, you've got the column fill with 1, 0, 1, 0, 1, 0. The ones means that we met all the conditions that you ask in the question. 0 does not meet. Okay. So now we want to count how many people satisfy those requirements. Unfortunately, AMBIT has no mechanism to count those, so they perform the bit count in the CPU side. Okay, but still very useful to perform those bitwise operation on there. And this is the result compared with the baseline. You can see they apply on the data with 2 weeks, 3 weeks, 4 weeks, 2 weeks, 3 weeks with different number of users. Okay. This is the recent or updated version of the paper in 2017. Remember, the updated one has AMBIT in the title. The older one, there's no AMBIT in the title. This is how you would know which is which. All right, because we didn't cover the last part, so that's why I have to go through it. Now we will start with the topic of today, which is how you perform really complex operation rather than just bitwise operation. All right? Hopefully that refresh your mind a little bit about what we studied last week. This is a very nice paper, close to my heart. We worked hard to achieve it. It was rejected maybe 3-4 times in the past. Okay, every year we improve something until it got accepted in top computer architecture conference. This is called Bluetooth. How many of you are aware about Bluetooth? This cartoon. Yeah, but the reason why we call it Bluetooth, there should be strong reason about that. There's something in the middle over there. Okay. Lookup tables. How many of you are aware about lookup tables? Why you are shy? How many of you are aware about lookup tables? 5, 6, 7. Oh, now almost everyone. How come you didn't know about databases and now you know about lookup tables? All right. So the key idea, still we want to leverage all analog operation inside the DRAM device. We don't want to add a compute core inside the DRAM. We don't want to do that. We don't want to add a small CPU inside the DRAM, right? We just want to leverage or exploit what is existing as analog operation on these 3 operations, just by using these 3. Activate, read or write, and pre-charge. By just playing with their order and their quantity, for example, we could repeat activate 3 times. Meaning that we are going to activate 3 different rows. Okay? We don't want to read them. We don't want to pre-charge. We don't want to respect that order of operation. This is what happened in AMBIT, right? We just send 3 ACT with different addresses to consecutive rows, of course, because we want to activate 3 next to each other. And then all of them will share the charge. And this is how we perform AMBIT. So we want to perform now much more complex operation. We don't want to do bitwise operation. How we do it? I already gave you the hint. What is a lookup table? What is the lookup table? Excellent. Did you hear the answer? Who want to repeat it? I want this side. Sorry? You can consider that, yes. How does it work?
I mean, you hash the index or whatever, that is the key, and then you map it to the data. So basically, you just do an O1.
You see? Now you know it. The last line. Someone from here. No, not necessarily to be unique. Now you said correct. Yeah, next time we'll do it that side. No worries. All right. So this is something nice. Just as a workaround, we cannot do complex operation. We just have that bitwise operation at the row level or row granularity. So we said, OK, we don't want to perform the actual operation. We want to do it still at the CPU. We want to do the all operation you think about, whatever the function. It could be really complex. The equation could be really with large number of operands. You perform it at the CPU. You save all the results in a table. That table, we call it lookup table, meaning that a table that we will look it up whenever we need the result. Okay, so we go to that table. Normally has 2 columns. You have index, okay, or a value as a selector. For example, we have here the C based on the selector. We choose the functionality, right? So you can thought about this as selector, where we select the function that we want to apply, or the operand to that function. And now when we said, I wanted the result of 1, then I have it ready over there. Just fetch it, done. So it's try to mimic the effect or the illusion of performing those operations. But in fact, I'm not performing them. I'm just storing them in here, over there, with all possible options. And whenever I need the input to be this much, I go and fetch the output from there. We'll see a few examples now. So the idea is simple. The user will provide me the input. Based on the input, I will look in the table and give him the result as if I am calculating it. But in fact, I'm just memoizing it or just fetching back from a table. So replace computation with memory accesses, Bluetooth lookup table query operation. Okay, and memory is very good in fetching those queries. If you know exact address of those results, you just send the address, activate, read, pre-charge, done. You get the output. Here's an example. We want to calculate the prime numbers, the second one, the first one, the second, and fourth prime numbers. How many of you know the prime number? Prime numbers. Should we do this again? Prime numbers. 1, 2. Who says 1, 2? Who says 1, 2? Wrong. Wrong. Big wrong. 2, 3, 5, 7, 11. Yeah, excellent. So what is the equation? What is the rule for prime numbers? Divisible by itself and by 1. Okay, so 1 is not considered a prime number. It will be problematic if we consider it as a prime number. All right, so we want to know the second. You already know the second and first, second, and fourth prime number. Okay, what is it? All right, so the user will give me this number. He knows the question. You know what he's looking for. He wanted the second, first, second, and fourth. But I'm going to build that lookup table. And remember, we calculated at the CPU, so there is no magic over here. We just calculated using traditional computers. Now, in the lookup table, we cannot ignore the other cases. We have to make it general. So it has to cover all prime numbers, okay? All of them, because we don't know the user is going to give me which number. You might ask for the 5th, for the 6th, for the 7th, for the 8th, and so on, right? So I have to build it from scratch with every possible option. Now I say, what is the first primary number? The first prime number? 2, right? So I just recorded there. What is the second prime number? 3, then 5, then 7, 9. 9? No, because divide by 3, right? 11, and then 13. Excellent, and so on. But remember, when the user asks me about first or second, in computer science, this is a waste of resource, because usually we start indexing from 0, not from 1. So when he asks for the first number, it's already the 0th number, right? The first one in 0. So that's why we have to convert those number. So the second is number 1, first is real 0, second is number 1, and fourth is number 3, right? This is just a transition between what the user knows and what computers understand, okay? Hopefully this is clear. Now, in the table, we still didn't compute the results, so let's add them together. 2, 3, 5, 7. And the table will look like, we don't really need that column in the middle, okay? Because this computer cannot understand, or can understand, but already waste our resource because start from 1. We don't want that index. So now let's merge it, move all together, and this is what really we need. Now, whenever the user asks, what is number 1? Go to the table, fetch 3. So here should be 3. 0 should be 2. 1 should be 3, and 3 should be 7. So we just tell the user, here you go. This is the result. Okay? This is really mimicking the illusion as if I'm calculating something. Now, of course, this is a very simple example, and we can perform in the CPU. We don't really need complex technology to do that. But think about really much more complex function. Remember, it's not function dependent over here. You just compute everything at the CPU. It could take ages to perform that. Once you get the result done, you save it in a table, reuse whenever you want. And this is why we call it complex operation. Now, the goal of this paper is to perform all of this inside the memory. So what we are going to do, just to store that table in the memory, we fetch based on the addresses, and that's it. But there is a fundamental problem preventing us from doing so. It's really not an easy job to just move that table and start querying it. Do you remember what I emphasized just before this topic? Just before we move to Ploto. What is the granularity that I can perform for AND operation or OR operation? Complete row, the complete row. And that will be my query size. So I cannot ask the lookup table, just give me the 5th number or the 6th number. I have to get a row of full numbers, okay? And how many numbers, it really depends on the size and how many bits I want to encode those numbers in. Could use 8 bits per number and so on. So let's see how we can perform it in real life. Remember, this is the question that we are looking for. This is the table, this is the input vector, and this is the output vector, okay? Now, this is traditional DRAM, nothing special. This is the DRAM subarray or the matrix. This is the row decoder, okay? This is the row buffer or sense amplifier, and this, the column decoder, the column decoder. And remember, all the time, we read one row, the whole row, we fetch it to sense amplifier, and then we use the column decoder to select which column out of that complete row, okay? What did we do? Let's do it again. Please pay attention. This is extremely important. What did we do? Copied all. One row contains one value. Full row. Each cell in one column repeated as many as can fit in one row, right? Why did we do that? Excellent, because at the end of the day, we access columns. We don't access rows, right? We access the row. We have to fetch column by column because the channel of the chip is how many bits? 8 bits. Excellent. It's amazing. I was not expecting someone would remember this. This is like 4 lectures back, right? Thank you. All right. And this is the huge challenge over there. We cannot query one number, but we can query the entire row. So to query the entire row, we still cannot query number by number, so we have to give a bunch of numbers. And now for every number, we don't know which row out of the table we are going to utilize. So for example, here, I request the first number. Second, here, I could request also the first number. Third, I could request the first number. But next, I'm requesting the third number. But I could request the 5th, the 7th, any number. So every time I have one number aligning with the column, I should have all the options, because I'm not sure the user is going to ask for which number, right? Over here, I ask for 1, 0, 1, 3, but I could ask for anything, any combination. And the layout we choose in Ploto is just to have vertical layout, okay, not horizontal. meaning that the complete table should fit in one column. But we repeat it many times because the granularity I have is for the entire row, meaning that vertically I should always check, do I have the first number over there? Yes, I should be able to answer that. Now, do I have the fifth number? Yes, I should be able to fetch that, and so on. That's why I repeat the lookup table many times in the DRAM. So every time I do one query, I directly fetch everything I need from all columns. Is it clear? Welcome, supper. Hopefully I will now. Yeah, you don't have to come. I appreciate that. Thanks. All right. So that is the first trick, that you need to have the data lay out vertically. So the entire lookup table in one column. Remember, the index, we don't really need to store it. Why? The index over there, the 0, 1, 2, 3, which is the first column in the lookup table, we really don't need to store it because it's already sorted, right? It's already sequential, meaning that if I'm asking for the first element, it should be in the first row. Second element should be in the second row. Third element, third row, and so on. Okay? Unless I'm really not utilizing the entire subarray. So this is an individual subarray just dedicated for lookup table operation. So the first row in that lookup subarray is already dedicated to the first element in the lookup table. Of course, but we enable. No, even worse than that. We will see. Even worse than that. It's not every time we turn on the machine, we need to load the lookup table. Much more than that. 1 million times, 2 million, 3 million, we will see that. All right. So now, how it will work? How we are going to access or send those queries to the lookup table. This is what I have as input vector. Let's imagine it exists somewhere. We don't need to know where it exists, okay? But assume we have it, okay? Now, remember, we access the entire row all the time. So we cannot say, where's the first element? Let's go to the second row and then fetch the entire row. We cannot do that. What we do is a mechanism called row sweep. Row sweep, meaning that you are sweeping all rows. You go from row 1 to 2, 3, 4, 5, 6. This mechanism already exists in the DRAM. You know where it's being used? We already discussed this many times in the past, where we need to access all rows and do something with them. Where we are accessing all rows one by one and try to do something to all of them. Sense amplifier. What do we need to do with the sense amplifier? Refresh the memory. You got the chocolate, right? Okay. Excellent. Excellent. So we know that the memory by itself leaks over time. So it's going to lose the charge. So we're going to activate or pre-charge every single row over a time interval, right? This is how we access the first row. We pre-charge it again. We access the second row, pre-charge, third row, pre-charge, and so on, right? So this mechanism, we call it row sweep because we are really sweeping or visiting all the rows in single subarray. And that's what was exploited over here. So let's sweep over the rows. Multiple copies of lookup table exploited the DRAM parallelism. And now we discussed this many times, why we copy the lookup table over columns. But you could come up with totally different mechanism of doing so, okay? So the DRAM parallelism, we discussed various forms of that. One of them, we said, we cannot access several banks in one chip, but we could access single bank over single chip, but many chips in the same clock cycle, right? So if we want to do more parallelism, we could divide that lookup table over multiple banks, like part of it in one bank in one chip, another part in another chip, and so on. So every time we just initiate one clock cycle, we're going to access all of them in the same time. you can think this is really left to your imagination, what kind of parallelism you want to achieve. We also talk about several channels, several memory controller, so you can access different them in the same time, right? But this is one way of doing parallelism over there. Now let's get back to our story. Let's activate the row sweep. We go over row 1. We fetch the entire row, the complete row from the lookup table. All 2s, okay? We bring it over there, and now we can access column by column. We have what we call a match logic. A match logic is responsible for checking the index that we have in the input vector along with the index of the row. We know that this is the first row because we are sweeping sequentially, so we are not missing any of the rows. We are not jumping back and forth, right? So we know that this is 0. So now we want to check the user input. Whenever it's 0, mean I'm interested in the first row. Give me that input or output that is stored in that row. So we check the index coming from the user. Is it 0? No, just skip. Then this is wrong. We go next. Is it 0? Yes. What does it mean? It means the user is interested in finding the first output, which I already have it copied multiple times. So now I said, OK, this is matching, meaning that go to the row buffer, give me 1 copy in the corresponding column. Give me 1 column in the corresponding column. How do I know the column index? It's already equivalent to the index of the query coming from the user. This is 1, so I store it in 1. Now, I continue to do that for all cells in that row. Okay, so still I'm doing this for only the first row. Remember that. Is it 0? No. Skip. Is it 0? No. Skip. Done. I'm done with the first row. Is it done for everything? No. Remember, I'm sweeping over all rows. Go to row 2 or index 1. Now fetch the entire row because that's the granularity where I can visit the DRAM subarray. Now the index is 1. I want to check the indices coming from the user. Is it 1? Yes. Oh, 1. Directly copy the column over there. So I copy 3 and 3 because that is also 1. But remember, I'm doing this sequentially because I can visit 1 column at a time. Now I go to the last one. No, it's not 1. So just skip. Now visit the next row. We fetch everything. We visit the indices 1 by 1. Is it 2? No. 2, 2, 2. No, 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 no. All of them. Don't fetch anything over there. Go to the next row. Fetch it all. Now go to the input user. Is it 3, 3, 3? No, 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 no. Last one is 3. Just give me the last column. And this is how I get the entire result for all the input coming from the user as a DRAM computation, or what we call in DRAM or using DRAM computation. Is it clear? Is it clear? How many of you understood what happens over there? Right? Good. We see the last row, all of them agree. That's perfect. OK. For those who didn't understand, what is the problem? Do you have any question? We can repeat it again many times. A CPU sending all those commands. Remember, memory controller is the only one responsible for activating any row, do the row sweeping, visiting any of them, activating this, activating that. Remember, DRAM doesn't know anything about those. Does not dictate what kind of operation I'm doing. Okay? Only the memory controller at the CPU is sending all those sequences of commands to the DRAM device to do now activate, pre-charge, read, whatever you want to do with that. Clear? There's really huge space for improving Bluetooth. Really. There is large space for improving everything, every choice. That is a very good design choice. I check the input vector first. I know how many I need to sweep over how many rows and how many columns, basically, right? Not only that, can I jump between the rows? Because I already know the addresses of them, right? I'm looking for something sequential. So first is really first. 0 is really, which is first one. This is second row. This is third row or fourth row, and so on, right? So I already know these addresses. So I could convert them to addresses, and I particularly visit that certain address and fetch all the columns from there. So there is still really large space for improving Pluto, but that is what is it. Now, there are some improvements in terms of the design. We still didn't talk how they really implemented in the DRAM device. Because remember, match logic does not exist, right? The input vector, we didn't talk about it, where it's stored, how the DRAM receive it. And the output vector, we don't have any choice over randomly picking the columns, okay? And there is one more thing which is important, but I will leave it for 1 or 2 slides. We will discuss it next, okay? Which is related to the row buffer itself. There's something really critical happening over there. But at least this mechanism really clear. If there is any question, it's important to discuss it now, because everything else will depend on that. Any question? Anything not clear? You understand why we duplicate the lookup table over columns? And why we didn't include the index as part of the data over there? All right, I assume this is good. Okay. Now what is important is how we actually implement it in the DRAM device. There are several changes happening to the DRAM device. Those changes can be severe, can be really major changes happening to the DRAM device itself. Let's see the first one, match logic. And you can think about the match logic that we use. So we are trying to compare the index of the row with the index in the input vector, right? Now the index is a number, right? It's not in a binary. Everything we saw in the example were in decimal, like 1, 5, 7, whatever, right? So the first thing is to convert that into binary, because the computer doesn't understand anything else except binary. So now the question is, how many bits do we need for those numbers? Let's say 8 bits, okay, for each of those numbers. Now we need comparators equivalent to the length of the row. The length of the row. Or could be the number of rows, okay? Could be also equivalent to the length of the vector coming from the user. Because by the end of the day, how many times we need to compare, it's the number of elements in the input vector. But how we implement it, we don't have any control over that vector, so we don't know it in advance. So the safe use case is just to replicate many times as we have in columns in the subarray. If we have 1,000 columns in the subarray, then for each column, we need that comparator, right? Because every time we compare with the index, with the number in the vector, and we see, does it exist? Does it exist? If so, we go to the corresponding column index, and we fetch that column. All right? Remember, number of columns equivalent to the row buffer, right? You agree on that? Number of columns equivalent to the row buffer. Because every time we fetch complete row, we go to the row buffer, which is sense amplifier. The second change is the row decoder itself. Because the row decoder, we need to let it know that the entire subarray is related to each other. Every time we have to do row sweeping, we have to go from first row, sweep over all of them. So there is minor changes to the row decoder in order to visit all of them sequentially and having a complete block of rows as one block of lookup table, okay? So we don't want to go outside the boundaries of that lookup table. So we want to really deal with those as single block of rows, regardless the number of these rows. But normally we assume that we fit it inside a complete subarray. That's the assumption we made. The third change we did is the row buffer itself. To do the row buffer implementation, we have 3 different designs. So you can forget about the text written there. I have many slides to show you the design itself of the row buffer. But remember what we were doing in the row buffer. We read the entire row, but we selectively choose out of that row. We could pass that column or this column or the next column and so on. Let's see how we can implement that in 2 slides. But now, hopefully you understand those 3 changes. Now let's see what else do we need. That's in terms of the device, the DRAM device, of course. The first thing, we need to enable this operation whenever a user will write a program. So we need to add APIs to the C program itself. One API could be something like this. I want to perform multiplication. This is the input 1, input 2, give me the output. And the bit width of each number is 4 bits. Okay? I could repeat this many times, and then the compiler should understand that I need a vector of data. So if I have many of those operations next to each other, I will take all input 1 and input 2, have them in one vector, for example, and send that vector to the DRAM. That will be my input vector, so I can fetch the lookup table and get all the values from there. Now, someone could ask, if I have more than input, how I could look inside the table. Remember, the lookup table has just 2 columns. One, the index, and one, the function. The function is easy to compute, just multiplication of 2 numbers. You could have a permutation of all numbers and multiply them to get that column. Okay? But for the first column, which is the index coming from the user, which one I will be used? Is it input 1? Is it input 2? That's what's coming from the user. 5 times 3 equal 15. So 15 will be stored somewhere here. But what would be the index of that value? What will be the index of? I need to choose one of them. Should I choose 5 or 3? If I choose 5, right, how I could differentiate it from 5 times 2? Column will be 3. Which column? I cannot do anything about it. I only have to choose one value as index and then use that index to revisit any row I want. This is how lookup table works. Cannot change that. I only have index of the row where the result is stored. But the user give me those 2 numbers. I want to multiply them. I don't want to do the actual multiplication because I will lose the essence of using lookup table, right? So I want to still use lookup table without performing the actual multiplication, but I need single value from the user per query. Every time I query, I need that single value, and then I will use it as index, visit the row, and give me the result. The answer is very simple. Array style. Okay, what should I do with the array? They always start with 0, but yeah, that 0 doesn't mean anything. I have to correlate it with something. I have to give it that meaning, right? The 0 doesn't mean anything. 0 is result of what times what. Could be anything. I could connect it to 5 times 3. I could connect it to 5 times 2. It's up to me how to arrange those outputs, right? So I could have the 15 in the beginning, and then I said whenever I get 5 times 3, it will be the first row. So one simple approach we use in Ploto. Is there any answer before I give the approach we use in Ploto? Amazing. Excellent. So this is a well-known approach in computer science. Whenever you have multiple data and you want to have a unique value to present them, that's really excellent. Think about images. You want to have a fingerprint of the image itself. You want to have a unique value always representing that image. The image has a large number of pixels, but you could represent it using just small number of bits. And that small number of bits will be really unique to that picture. This is what we call as binary encoding or hashing or any of those techniques, right? You just hash the entire book and you give it a unique signature. Now, every time I need the book, I don't ask the computer, hey, here is page 1, here is a page 2, here's page 3, and so on. No, done. This is my signature. That represents the book. And likewise, we need to build any kind of representation for those two numbers together. It doesn't matter which is which. So it could be 3 times 5, 5 times 3, same thing, right? So we use something like represent each of them in binary, and then or all these bits together, or and all these bits together. It's up to you to use what kind of combination. You want to shift the first operand first, so leave it in the second part of the register. Have the first operand, for example, in the beginning of the register. And then you have a register having 3 and 5 all together in the same array. You could do that. Now, all of them will be represented as one number. You could query that number, and you should get the output as is. Now, that is, again, there is a lot of space for improving this representation. It's up to you how you choose, what is your space, how many numbers you have, how large, is it like in millions, then how many bits you need to represent each number. That will be impacted by the space that you're looking for. If you're looking for a large number of numbers, you should have unique signature for all these options. Otherwise, you will have a collusion all the time you query, because single signature can represent multiple numbers, and then you don't know which solution is for which input values. Is it clear? How many of you used hashing before? You see, all of them, almost all of you. Whenever you transfer a file from one place to another, you do, for example, MDF5, right? This is a way of verifying that the file you received was correctly. So you represent the entire file using a long hash, and that hash will represent that file. And then when you receive it, you just use that hash to check the validity of the file, whether it was corrupted, anything missing from the file, and so on. Why we were talking about hash? Yeah, please stay awake. Try to connect all these points together, okay? I see someone with cola, someone with coffee. Hopefully you use those to stay awake, okay? All right, what is the next changes that we need? Whenever we enable something in C, remember, the compiler needs to understand them, so that will be converted into, before the ISO there is something, assembly, right? Assembly machine code, and machine code will understand the hardware. And what is ISA? Instruction set architecture. What does it mean? You can think about it as the smallest block in the microprocessor or the CPU itself, okay, the ALU. What kind of operation is enabled in the processor, okay? Or what kind of operation we understand from the CPU, or the CPU can understand, basically. So think about this. This might be the simplest function that's done in the processor, but you can think about and, or operation, and many more, okay? All of those might be already integrated in the CPU. So you have multiplication engine, for example, or you could achieve multiplication by shifting the number. So you can have shift engine inside the CPU, but not multiplication. Because remember, multiplication is really expensive to be implemented. Normally, we implement it by performing shift operation, for example, if we are looking for multiplication of multiple of 2. If you multiply a number by 2, any number times 2, how we perform that without doing multiplication? Just shift to left, okay? Remember, the binary numbers are 0, 1, 2, 4, 8, What is next? 16, 32, 54. Excellent. Now you are awake. Remember the 0, you don't really need it because this could be 0 or 1, right? Okay. Now, if you shift to the left by 1 step, you're multiplying by 2. Shift by left, you multiply by 2. Shift to the right, divide by 2. This is one way or one hack where the CPU can perform multiplication or division really quick. So sometimes you don't have multiplication instruction as ISA, but you do have shift to the right, shift to the left. So now who's doing that? The compiler understands that the user wants multiplication. OK, I don't have multiplication. I'm going to convert the operation into the ISA. OK? So we also introduce some new ISA that the compiler needs to understand and convert any user input operation into those. And now we also introduce a new sequence of commands in the controller. Remember, anything we want to change in the DRAM, we have to directly change the memory controller because the memory controller is going to issue all these commands to activate or read or anything related to the DRAM. So we introduce our own set of operations in the memory controller. Whenever we want to do flow to something, we directly activate that sequence of commands all together as one set. We have several number of those operations, so they're listed in this table if you are interested in doing so. And maybe someone could ask me why we need those bitwise logic operations. We have not, or, and so on. I thought the idea behind lookup table is not to perform any operation. We want to do everything in the lookup table. So while we are implementing here a bitwise or, bitwise and not, and so on. So I'll leave that up to you to read the paper, but I will give you a short answer over there. Think about it as when we discuss how to build the hash value for these two numbers. Okay, we still need to do some kind of bitwise or and shift one of the values to the right so that we can fit both of them in one register, for example, this way. So the 3 will be 1 1 0 0 0 0 0. The 5 will be 1 0 0 0. Or maybe 1 here. That's 4. So that's 5 and that's 3. If you want to fit them in one register, you just shift one of them to the right. So you can fit it over here. And then you fit the other. Then you have that as one number. Then you can query that. So that's why we need the shift operation over there. And then you do and, for example, or whatever you see valid for your problem. Okay, that's example on multiplication, but maybe for something else you need another operation. That's why it's all of them provided in Pluto. And there is a visualization for the problem here where you can see that there are 2 inputs coming from the user. We convert them into one input. We use that to query the row of the lookup table. Then we got the output from the DRAM. If you're interested, read the paper for the details. This is an extremely important part of Pluto. We talk about changing the row buffer itself, or we call it a sense amplifier, right? But what kind of changes we can do? Now, we use 3 different designs in row buffer, okay? This is really important. Please pay attention. The first design, we call it BSA, buffered sense amplifier, meaning that everything here is as in normal. We have a word line, bit line. We have sense amplifier, but we add something to the sense amplifier itself. We have FF, mean flip-flop, right? Whenever we talk about flip-flop, we talk about storage unit. Every time you want to store any bit, use flip-flop. Flip-flop is really quick. In 1 clock cycle, you can store anything, right? It doesn't leak, doesn't lose its value. If you want something cheap, you can use capacitors. So you can add capacitors over there, but good luck maintaining that charge. You need to deal with it separately, keep recharging it, refresh all the time, and so on. That's a lot of overhead. So we decide to use flip-flop. Hopefully now you understand why I use flip-flop. It's just a storage unit for a single bit. However, we don't want to store all the time. So we fetch the entire row from the lookup table, but we want to selectively choose which column we want to out of that row, right? To enable that, we need a transistor or a kind of switch to read or not read, to store in the flip-flop or don't store. When to enable that switch? Raise your voice. Yes, Jahil? Same thing? Whenever it matches the input. It refers to column. You are very close. The index of the row, right? So the column, we already know it because all of this structure in one column, right? This sense amplifier for single bit in that corresponding column, right? Which is coming from the bit line. So we already now, we are in this column, right? We don't need any index to verify that. But we need to know, is the input coming from the user matching the index of that row? Meaning that, is that row that I need to fetch from lookup table or not? As simple as that. If this is the one, then I want to store it somewhere else. So I enable that switch, meaning that I close the circuit. So whatever I'm storing in the sense amplifier, I'm going to move it to the flip-flop. I'm storing now the entire column, right? Any question? Because whenever I enable one, I'm doing row sweeping, right? So meaning that I'm visiting that row, meaning that I'm activating that row. If I'm activating something directly, I'm sharing the charge with the sense amplifier. So everything I read in any line will go directly to sense amplifier. Remember, sense amplifier is bitwise. So for every memory cell in the DRAM, I have a corresponding sense amplifier over there. So I'm storing only single bit from that row. And I have row of them. That's how I store the entire row in the sense amplifier. So how many flip-flop do I need? Excellent. How many bits I store in the row? That should be how many flip-flop do I need. For every single sense amplifier, I need one flip-flop to store that single bit. Okay? Any question? Okay. Now let's see the second design. Now remember, if I'm storing something in the sense amplifier and I don't play with it, don't interrupt it, okay? So I can do pre-charge and charge over there again, and that's it. So this is how I maintain the row itself. Now let's see another design. So I'm connecting the memory cell through the bit line through the sense amplifier. But now I said, okay, I'm fetching the entire row, but I don't want to connect it to the sense amplifier because it's not relevant to me. I have the, maybe I can use another color. Can you see something in here? Or the screen blocking? Good? Okay. So think about the entire row buffer. Instead of fetching the entire row and then go column by column and choose which one to enable, okay, I could preventing storing the entire row and only allowing for the values that I'm interested in to pass through the sense amplifier. In this way, I'm doing earlier column decoder. So I'm bypassing the sense amplifier and kind of I'm applying the column decoder somewhere here. So is this the matching logic that I'm using, or is this index match the user index? If yes, I allow the column to pass to the sense amplifier. If not, I don't allow. This way, I could control what is coming to the sense amplifier through the logic gates or the logic, match logic, right? If the match logic says, yeah, those indices match each other, then I allow the bit to go to the sense amplifier. And by the end of the day, everything in the sense amplifier is the thing that I need, which is the output of the lookup table, okay? But there is something really important here. Whenever I play with the sense amplifier, what do I do? What do I do? how I can do pre-charge if I alter with the content of the sense amplifier. If I selectively choose what to store in the sense amplifier, I'm taking part of that row, then part of the other row, part of the next row, part of that row, right? Because I'm doing row sweeping, and every time I choose different column through the column decoder, I allow part of the row to pass, then I go to another row, I got the new content over there, I allow to the next column to pass, and so on. So I have really weird content in the row amplifier. Now, how I can do pre-charge? If I pre-charge the content over there, I'm altering the content of the lookup table, which is I'm storing the output I have in the sense amplifier into the lookup table, then no longer the lookup table is valid. What should I do? Think about it. So the problem is that the lookup table now looks different, looks something weird. It's already altered, because anything in the sense amplifier, when I do pre-charge, I directly rewrite or overwrite the lookup table itself. What should I do? You remember, Naim? What did you mean? Yes, please, Jan. I don't pre-charge, but you are going to do that. Remember, there is row sweeping. You have no choice. You have to visit everything, and every time you change the sense amplifier, every single row you might change one column in the sense amplifier. So every time you have different content in the sense amplifier. If you want to pre-charge all the time you visit any row, then the entire lookup table is different now. You remember what we said about loading the lookup table? How many times you want to load the lookup table now? Excellent. Every time we believe that we change the sense amplifier, we need to load the entire lookup table again to the memory. Every time, regardless if it is every query, if it is every row sweeping, if it is changing the sense amplifier, which is not necessarily correlated to sweeping the rows, because you might visit the row, but you might not choose any column. Depends on the indices and their input vector, right? And that is the drawback of that design, that you really need to keep loading the lookup table every time. What is the cost of doing so? It depends. What is the size of lookup table, in which subarray you can fit it, and so on. All right. Another possibility to do so is the third design. So now we have the capacitor over there, but we have something weird. We want to ignore the bit line totally. We don't want to connect the bit line, except in one case where the match logic is telling me this is a useful memory value in the cell. So in the first case, I wait until I read that cell, and then I decide if I want to use it or not. In the second case, I avoid the sense amplifier, and I decide before I send it to the sense amplifier. Now I want to do much earlier step and avoid even sending it to the bit line itself. I don't want to send the value at all outside the memory cell. Okay? So I add a controller over there before connecting the cell to the bit line itself. Now, if it doesn't match, I don't really need to share it with the sense amplifier, meaning that I'm not sharing the charge, right? Because there's no connected bit line. So I'm not altering the value of the capacitor. So I don't really need to do pre-charge at all. So the value is still there. It's not shared. It's not reduced. I'm not sharing it with something else. So I don't really need to worry about pumping it again, right? But remember, it leaks over time by itself. So I still need to refresh it. But at least I don't need to pre-charge. So the sequence of those commands, I can play with it, and I don't really need to pre-charge again. So I add the controller over there, connected with the bit line, and whenever I see a match, then I connect it, and then I read it in the sense amplifier. Now there's no problem with the pre-charge as the previous. Now the question is, which one is better? Which one to choose? Which one to use? Apparently, you can see there is fundamental differences. For example, it's here and here. It's all about transistor, just gatekeeping the signal whether it goes this route, that route, and so on. But over here, it's much more than that. We add that transistor, but we also add flip-flop, which is taking area and takes some of the energy because it needs a clock cycle to operate on, right? Which one is better? Not only that, the second one, I'm also altering the sense amplifier, meaning that loading the lookup table all the time. Every time I alter, load the entire thing. Not single row, not single cell, the entire thing. That's really a strong question. We got a lot of questions of those from the reviewers. So you can see we use 3 metrics to decide. One of them is performance, energy efficiency, and area efficiency. If you look at the first one, you will see very good in terms of performance, very good in terms of energy, but area efficiency is bad because of the flip-flops taking that space. Now, if you look at the second one, it's good in area because just transistor next to the sense amplifier, and that's it. But in terms of performance, it's very bad because we need to load the lookup table all the time. And in terms of energy, is not efficient because loading the lookup table will take a lot of energy to send those data again to the DRAM. Now, when we look into the third one, we will see performance is really good since we are not reading at all and no need to pre-charge. We are not sending the charge to the sense amplifier even. So just we are keeping the charge in the memory cell, except if it is matching, we send it to the sense amplifier. So in terms of energy, it's really good, but in terms of area, it's really bad. Why? This really deserves a chocolate. I swear to my wife that this time I'll go back home with no chocolate. So please, I need someone to take it. Why? In the third case, it's really memory. What memory? What memory? You are very close. Clarify. Number of bits to store. Yes, what do we do with it? What do we change in the memory cell? The third design. Do you remember it, or do you want me to show you the slide where we have the 3 design? No, no. Yeah, very close. We changed something in the memory cell. What is it? Maybe I can do refresh. Just mind refreshing. What do we do next to the memory cell? What do we have there? Switch transistor. It's added to what? This is what makes the trick. Do we add it to the bit line, or do we add it to something else? Who said capacitor? Yeah, I said this side is really amazing. You know, they are not participating, but when they do, yeah, you can have both. You deserve it. We add it to the capacitor. Capacitor is a memory cell, meaning that we are not doing the change to the sense amplifier. Remember, we could have the memory subarray, which is a huge. This is too many memory cells. We have in every row like 1,000 memory cell, and we could have like 5,000, 8,000 of rows. The sense amplifier is only single row. So if we do any changes over there, at most is 1,000 of those items. If we add flip-flop, it means only 1,000 flip-flops. But if we change anything in the memory cell, it means how many times do we need to add that? The size of the entire array. One example, this could be 1,000, 20-something, and this is 8,000 normally, or so. So if we change anything in the memory cell, we need this many times of that item, which is 1,000 times 8,000 of transistors to be added to the entire lookup table. Any changes to the sense amplifier is really cheap to do, right? It's something simple. You just add 1,000 items of those. As simple as that. You understand why the area is really not good? Is it clear now? So if someone asks you which one is better, you tell them what is better. Okay, define it to me. Is it in terms of area, energy, or performance? Hopefully you understand why this is really important and why I'm trying to teach you these very small detail, but in fact is really essential if you are interested in doing research in this area. Because you really need to worry about all of these aspects. You cannot just simply assume that, yeah, we add this to the DRAM, we assume this, we invent this to the DRAM, you can add anything you want, and that's it. You really have to understand what kind of effect it has in terms of those, or maybe something else, like the price of those items that you are adding to the DRAM. Not only that, there are something important with the mechanism, working mechanism of the DRAM itself. You have to respect some timing constraint. We talk about refresh interval, for example. So in that interval, you have to stop everything and keep refreshing the entire DRAM, for example, to maintain the correctness of the data stored over there. Is it clear? So the Pluto designs cover a broad design space and provide different performance, energy, and area efficiency. Yeah. Now, when we talk about the overhead that you are adding, here's a summary of what's being added. So this is the first design. This is the baseline, which is the original DRAM. Okay, the original DRAM with no changes. This is the first design, second design, third design. And what you saw over there is the things included in the DRAM itself. How many DRAM cells, the local driver, match logic, match lines, sense amplifier, row decoder, column decoder. Some of them were invented or added to the DRAM. That's why you don't see them over there. For example, the match logic is something added to Pluto. Still have 8 minutes. Come on. Not only 8 minutes, I could keep you for 20 minutes. Okay. Now, the important question, what is the overhead of each of those designs? Like we said, the area is, okay, getting bigger, the area is getting smaller, this is efficiency in terms of area, in terms of power, and so on. But in terms of numbers or percentage, what is the added area overhead? So the first design, we add about 10% to the area of the DRAM, okay, because we are adding the flip-flops. How many of them? Remember, we add only to the sense amplifier, meaning that only 1,000 of them. But the flip-flop is already big because 2 latches. Any D flip-flop is built using 2 D latches. You know that, right? No? How many of you know latches? D flip-flops? No D flip-flops? I thought you were really top in digital design just a few seconds ago. How many of you know logic gates? Simplifying logic gates? D flip-flops? You don't know D flip-flops? How you were designing counters and timers and clocks? You should use them with the logic gates, right? How you synchronize the clock, the input. Okay. And maybe I should teach digital design next semester. All right. Yeah, the first design is adding 10% to the area overhead. The second one, 16%. And the third one, 23%. 23 is real significant. And hopefully you know now why. Why is that? Because any item you add to the memory cell is really much more expensive than what you add to the sense amplifier. This is the whole array. This is a single row. Okay. Do I still have more? Oh, I have 2. Why do I have 2? Okay, we should have 2 questions now. Yeah, so we try Pluto with the first design, and now the second design, and the third design on CPU compared to GPU compared to processing near memory. Okay, so you can see the average speed up with different designs. Of course, we said this is very fast because we really don't need to load the entire lookup table every time we do a query. But also, We don't need to send a charge to the sense amplifier, so we keep it in the memory cell. That's why it's the fastest. Now, when we look about normalized area, the same story. So the speed up averaged over area. When we look about energy consumption, so this is average energy saving, meaning that the higher number this is in terms of CPU and GPU. And this is what we can grant to chocolate for. This is really important aspect. Now we talk about those numbers. If you want to multiply two numbers together, you have to merge them into one signature or hash value and send that to the lookup table, right? Hopefully this is clear and everyone understands that. Okay, perfect. Now, how many bits do we need to encode the two numbers together? So here, we need 3 bits at most. Here, 3 bits, right? So we can use 3 and 3 and 6 bits, right? As simple as that. But it's always best if we have the granularity as 2 to the power of something, okay? So that's how we deal with computer, always multiple of 2, 4, 8, 16, and so on. So we try here different query sizes, like if the query of single bit, okay, like yes or no question, 2 bits, 4 bits, 8 bits, 16. Remember, this is not the entire vector. This is every number in the input vector. Okay, so if the user asks for the prime numbers, give me the first one. Now, the first one, should I encode it in 2 bits, 3 bits, and 4 bits, and so on? So it's not about the entire input vector, but every element in the vector. So we vary the number of bits all the way to 1024, meaning that every one element in the vector is 1024 bits. Okay. Now, what do we see over the 3 designs? We can see the throughput, which is number of operation per second, meaning that the higher is the better because I'm able to perform many operations in 1 second. Okay. Now, regardless of which one is better in terms of the throughput out of the 3 design, what I want to focus on is the scaling of the throughput. With the more increasing the number of bits, I am. What happened with the throughput? No, there is lady said it first. Who said it first? What did you say about throughput? Yes? Why? Excellent. But why? Why, with increasing the bit width of those elements, I'm losing the throughput? Someone else could also help. I have the last one. More space. What do you mean more space? We are not actually storing them. We are not storing these input values. We are using them to query. Okay. But there is something related to storage, but not about these elements. What I'm doing with these elements? What I'm doing with them? Lookup table, right? So I use the number. If the number with 2 bits, meaning that I need to check only 2 columns, right? Only 2 columns. Each column storing 1 bit. Now, if 1,000 bits, then I'm checking 1,000 columns just for 1 element, just for 1 lookup, right? So you got why we are losing the scale. Every time we increase the size of 1 element, I'm reducing the possibility to fit more queries in 1 vector. So if it is 1,000 bits, then 1 element in the vector, then I'm able to do 1 query at the time. That's it. But if it is 500, then I'm fitting 2 queries in the vector, so I'm able to perform 2 queries at the time in parallel. Okay. Now you can scale it to 2 bits, for example, how many queries I could fit in parallel, and so on. That's why the performance is really high when you consider low number of bits for each of those elements. Now, in the paper, we try for 4 and 8, but you could still like achieve good speed up with 16 bits, as we can see. And that's something configurable. Now, we try out something else is, for example, can we divide the query itself into multiple bits? If we have, for example, 16 bits query, can be divided into 2 queries, one of them 8, one of them 8? What is the difference between a query of size 16 and 2 queries of size 8? The throughput increases. Why? The throughput increases per number of queries. Yes, this is 2 queries in the time, but this is 1 query. But at the end of the day, they are doing the same thing. This is 16 bits. This is 2 8 bits, but serving the 16 bits, meaning that just same query. Send it sequentially. Can you elaborate more? Think about the size of the lookup table.
The half.
Excellent. So now, when you consider 4 bits only for the index, what happened with the number of rows in the lookup table? It's smaller, because the permutation I can fit in 4 bits is very limited, right? Which is 2 to the power 4, right? That's the size or number of rows in the lookup table. Now, if it is 8 bits, 2 to the power 8. Now, which one is more expensive? Right? You can do the math and see if I use 2 of these or 1 of that. Not only that, I can also move one of those tables into another subarray and then perform something in parallel for those 2 tables. As I said, there is really a lot of improvement that you can perform in lookup table or Pluto. And I wish like someone would take the initiative and try to really improve Pluto itself, but requires a memory simulator to modify the DRAM substrate itself and try to do something else. I think by next lecture, we might revisit those kind of simulators, how you can play with the DRAM, same as we did with the cache. We don't have a simulator for the cache, but we do have that Excel sheet where I ask you to modify the numbers and give me the best design that you could fit. I think we rewarded those 3 students who solved the Excel exercise about 5 points or so for each of them as bonus. How many of them solved the Excel sheet? So Nancy, one of them. Yeah, 3 of you, I think. Yeah, each of you got 5 points, okay, as a bonus. Next time, we are going to talk about still something relevant to processing in memory, but we will see different flavor, like about 3D stacked memory instead of just working with the DRAM. I think no more we have examples on the DRAM, but I will give you a lot of papers if you're interested in this topic you can read in your own. Okay? Can you raise your voice? Live demo for the simulator? Yeah, I think you might find a line. We will discuss next lecture. We will see that. Okay? All right. Yeah, that's a great question. Thank you so much, everyone. Please, let's wait.